section 7.3 is titled Repeating Decimals. And what we've been doing so far are what were called terminating decimals. One of the section titles called them also finite decimals, like they ended. There was a relationship that we discussed between fractions and decimals that talked about when a decimal would terminate. Do you remember what it said as the way that we could decide if we had a fraction, what we could do to know whether or not it was a terminating decimal?
If one factored, it was only 2s and 5s.
Yeah, so if when we reduced it first and we looked at the denominator factors, if the factors in the denominator were only 2s and 5s. And that was actually theorem 7.1. So theorem 7.1 says if the simplified, or reduced if you like that one better, fractions denominator has only factors of 2 and or 5. And if it has anything else, then it's not going to terminate. So what happens if we actually can't terminate a fraction, right? What is that going to happen then? Well, if that happens, then we're going to have to look at it in a different way. So if the fraction is an integer over an integer and does not repeat, I didn't say it right. It does not terminate is what I meant to say. Then it will repeat. Oh my goodness. It does not terminate. Then it will repeat. Knowing that it will repeat is helpful because sometimes it doesn't always repeat immediately, right? It might not repeat the same digit over and over and again. Like it might not say 3, 3, 3, 3, 3. It might say 6, 9, 5, 4, 3, 2, 6, 9, 5, 4, 3, 2, and it might take a lot of digits before the repeating starts. That's a possibility. But we know that it will start. So here's an example of one. We're going to look at the fraction 1 over 24. So as we look at the fraction 1 over 24, how do I know it is definitely not going to terminate? Yeah, if I try and factor 24, it's going to have a 3 in it, right? Yeah, and it's reduced. I mean, like there's nothing I can reduce to make that not happen. So it will, in fact, be repeating. So I can't have 21 going into 1. So we'll add some zeros along the way here. 24 does not go into 10 either, but so we've got a 0 up here as well. So in the 10th place, there's a 0. But 24 will go into the number 100. How many times?
4.
It'll go in 4 times. And what is 4 times 24? It is 96. Good. And at that point, I have a remainder of 4, right? And I'll bring down another 0. Does 24 go into 40? Once. And then I've got subtracting a 24, leaving me with 16. And so I'll bring down another 0. Because so far nothing's repeating on top. Right? I've got a 0, a 4, and a 1. So I have a number 160. How many times will 24 go into 160?
6.
It will go in 6 times. What is 6 times 24? 144. And what is it when I subtract 160 minus 144?
16.
I have 16. Okay, I could continue the process. I could continue to try to do this, but at some point you're going to recognize that the 16 remainder here that you got is another repeating part, like the remainder itself repeated. And the first time the remainder repeated is the first time that my numbers on top are going to start repeating as well. So if you don't see it right here, that's okay. You will very quickly because you'll try and get another 6. And you'll be like, now wait a minute. If you go one step further, it becomes very, very clear and obvious. So what we do is we take the value that we had before we actually had anything repeat, and we put a bar on top of the repeating digits. This time there's just one digit that's repeating, namely the 6. So our solution for our repeating decimal here is 0.0416 with the 6 only repeating. So far, so good? Okay, a little bit of vocabulary. We call this type of number our decimal or repeating decimal, and the repeating block of digits are called the repeat end. So in this case, the repeat end would just be the 6, because that's the only repeating block of digits. Note, I expect to see division when you convert these, just like I did in the last section. I know your calculator can help you out, and by all means use it. But you're still going to show me a little bit of work of what the division looks like. Okay? One of the very useful benefits of division for students as they're coming up is that division helps them learn more about multiplication. And knowing that a multiplication division helps them immensely when they're reducing and combining in things with fractions, even if they're still working in the decimals or whole numbers. That's immensely useful. So we're going to do another example. Same description, right? Find the decimal representation for 29 over 99. And 29 is prime, so I know that it doesn't go into 99, so it doesn't reduce. 99, if you tried to factor it, will have factors that include both 3 and 11, neither of which are 5s and 2s. They're prime, but they're not 5s and 2s. So this is definitely going to be repeating. It doesn't go into 29, but it does go into 290. So how many times does 99 go into 290? 2 times. So what is 2 times 99? Mm-hmm. And what do we get when we subtract that? 92 is right. So we'll put a 0 and bring it down. 920. So how many times does 99 go into 920? Goes in 9 times. 9 times 99 is, I don't have this written down. What do you have for 99 times, what is it? 99 times 9.
891.
891. Lovely. And when we subtract, what do we get? 29. So again, if you don't notice it here, it's okay. But 29 was the original number we divided by, or divided with, right? It was the original number underneath. So it's the equivalent of having the original piece right here repeating itself now. Which what that means is that this whole block of things that we just did, where we got a 2 and a 9, is going to repeat. And if you don't see it yet, just do it a couple more times, and very quickly you'll see, oh, look, it's 2, 9, and then it'll happen again. So on this one, we have the 2 and the 9 both that are repeating. So the bar goes over both of them, like that. Now you might have, depending on the kinds of math things that you've done before, been able to tell me that this is 0.29 repeating looking at the fraction they gave you. It's a possibility. And there is a relationship and a reason why, if you have seen that before, that happens. And we're actually going to explore that a little bit, but doing it from a different perspective. So what we've done so far is we've taken fractions and we've turned them into repeating decimals. So what we're going to do next is we're going to take repeating decimals and turn them back into fractions. Okay? So this repeating decimal has the 6 and the 1 repeating. And I can tell you right now that it is sort of the flip of this particular problem. This was a 2 and a 9 repeating. It was 29 over 99. This is a 6 and a 1 repeating. It's going to be 61 over 99. I mean, that's what it's going to be. But I want to show you how to show that that's the case, because it doesn't always work out that way. Sometimes it's 1 digit that's repeating, or sometimes, which we'll do in a minute, or 3 digits that are repeating, and so forth. Okay? So we're going to first call our number n, and we're going to write down the 0.61 with the repeating. Okay? So we're just going to write it down. Give it a name, write it down. Now, however many repeating pieces there are, so in this case there's 2, right? The 6 and the 1 repeat over and over again. There's 2 repeating pieces. We're going to multiply by that power of 10. So times 10 squared, which is the number 100. So we're working with powers of 10, or you can think about it as multiplying by a power of 10 that has the same number of zeros as the numbers that repeat. I've got 2 zeros because 2 of my numbers repeat. So on the left-hand side, this becomes the number 100n, or the value 100n. On the right-hand side, what I'd like for you to see is that if you take 6, 1 repeating and you write it out a few times like this, and if you multiply by 10, it moves the digit 2 to the right, right? That's what it gets. And the 6, 1 repeating is in the same location that it was before. Do you see that? After my new decimal point, it still says 6, 1 repeating. So over here, as this happens, and this is the reason why we multiplied it by, say, 100 and not by 10 or 1,000, I actually end up with the 6, 1 repeating in the exact same location with some additional numbers now in front. There's a 61 in front, but the 6, 1 is in the same spot. Okay? Super important that the 6, 1 is in the next spot, because the next thing we're going to do is we're actually going to subtract the original value that I was given. That's this, all of it. So I subtract the n from the left because it has n's, and I subtract the 0.61 repeating from the right because it has the numbers with the 6 1s in it. And lovely things happen because the 6, 1 lined up. So it continues to go on forever, but they line up perfectly, so they subtract themselves out. So what do I have on the left? Well, I had 100n minus n, so that's 99n. Right, we're not division, it's subtraction. 100n minus n would be 99n. And on the right, I simply have 61. And then lo and behold, when I divide by my 99, the expected answer from when we talked before comes about. 61 over 99. Okay, but this is an actual argument for why that's the case, not just saying, hey, look, there's this really cool pattern and it always works. Because it doesn't always work. Because it doesn't always happen that all the numbers repeat. For example, this one. This time, the 6 and the 1 don't both repeat. It's just the 1 that repeats, right? And that makes it trickier. That is to say, it's not 61 over 99 on this one. It's just not. So we're going to solve the problem in the same way that we just did before. We're going to write down n equals. We're going to write down the 0.61, but only the 1 repeating like that. This time, however, there's only one number that repeats. So I'm not going to multiply by 100 because that had 2 zeros. I'm only going to multiply by 10 because I only got 1 0. Okay? If I had 3 numbers repeating, I would be multiplied by 1,000 because I'd need 3 zeros in my power of 10. Are y'all with me? So we're going to multiply by 10 on both sides. So clearly that gives me 10n over here. And you don't necessarily have to write this out, but I kind of think, at least for right now, it probably will help if you do. When I multiply this by 10, that 0.61 repeating will move the digit over here. And while it is true that this is 6.1 repeating like this, that's not helpful. I want the 1 repeating to be in the same spot that it originally was. So instead, I'm going to write the second one out and put the bar over the second one. Okay, that's not how I'd ever leave an answer. Right? I mean, it's not the reduced or simplified way of writing it. But for what I'm doing next in the problem, it is the most helpful way to express it at the moment. So I'm going to take that digit, or that numeral, 6.1, with the 1 repeating like that, and write that on the right-hand side. Okay, so the next step is always to subtract the original n that I was given, or that I created. So n on the left, and 0.61 repeating on the right. And again, the goal and why we did the repeating where we did is because I want the repeatings to line up so that they reduce, they cancel out, they simplify, they disappear, whatever word you want to use. They're gone. Now, 6.1 minus 0.6 still gives me a decimal, but it doesn't give me anything repeating. So on the left-hand side, I have 9n. What is 6.1 minus 6? 0.6. Sorry, I said that wrong. 6.1 minus 0.6. 5.5. Okay, everybody good with that? Okay, so what would my next thing I need to do be? Goal is to solve for n.
Divide the number.
divide by 9. Now, unlike the last problem, I'm not actually done here. Does anybody know or see why? Yeah, I have a decimal inside of a fraction. That's not a reduced form of anything. Now, we learned back, I can't remember which section it was in now, I think it was in 7.1, that I'm allowed to multiply the top and the bottom with the tens. I talked about that at least in that section. We learned it back in chapter 6. But actually, that'll move the decimal on top, and it'll add the denominator to be a 90 now. So I can rewrite this as 55 over 90, and that's closer, sorry, not 99, 90. And that's closer, but it still can reduce now. How can this reduce now? Yeah, they happen to be both divisible by 5. So that doesn't happen at every part of a problem, but it did on this one. So 55 divided by 5 would be 11, and 90 divided by 5 is 18. Now, I'd like for you to grab your calculator real quick to check this. You can always check your work on these. The way you can check your work is you can take the final answer you got fractionally speaking, right, 11 over 18, and you can put it in your calculator. And if you did it all right, and that's really the correct answer, you should get 0.6 with a whole bunch of ones after it in your calculator display screen. Did it work? Yeah. So that actually proves or verifies to you, really, that the process that you did actually created what you wanted to do. Okay, I've got one more. Same directions, but something interesting is going to happen on this one. So all the processes are the same. I have n equals, and I have 0.9 repeating. Okay, how many numbers are repeating? Just one. So what will I multiply both sides by? 10. 10 to the 1, which is 10. Yep. So on the left-hand side, it becomes 10n. On the right-hand side, which would have looked like this, right, and continuing on, I move the decimal 1 point, and I will get a 9. And then I want the 9 repeating to line up with the 9 repeating I already had, so the first 9 after the decimal point will be the repeating place I locate. Okay, everybody good so far? It's just like our last problem. What's my next step? Yeah, subtract the original problem, n. Now, sometimes n is a larger number than just 0.9 repeating. It might not be a decimal. It could be like 2.7 repeating, and you could subtract 2.7 repeating. You're subtracting the whole thing of the original number you were given, whatever that was. So in our case, it is 0.9, like so. So on the left-hand side, I get 9n. On the right-hand side, those 9 repeating pieces line up. And what in the world do you get on the right-hand side? 9. What would we do next? So what does n equal? 1. It is absolutely 100% true, provable, that 0.9 repeating equals 1. Emily's not sure. So that's kind of a crazy thing to learn. I remember when I was first discovering that and thinking, wait, what? Yeah, 0.9 repeating is equal to the number 1. It's exactly the same. Okay? Crazy, crazy stuff. So we're going to look at a couple other things in this section regarding the repeating decimals and operations and things we can do with them. Number 6 actually wants us to find a decimal between 0.9 repeating and 1.1. But you actually just learned that 0.9 repeating is equal to what? To 1. So if you want any decimal between 1 and 1.1, can you give me an example of 1?
1.02.
1.02 is a lovely number between. Now, that's not an easy question for a student to answer if they're first looking at these, because it doesn't really look like there's any space between 1 and 1.1. So if you're looking at that and you're not sure, or you're trying to show a student and they're not sure, what might be helpful instead is to add some digits on the end to give you some space, right? So you could always do that. If I have the number 1.00 and the number 1.10, and I'm looking at the last two digits, now you can see space between them that you maybe didn't necessarily see before. So 1.02 is definitely, between them because the 02 is between 00 and 10, right? I mean, that's the idea. So can you give me a couple more just so that we have a few listed? 1.07. 1.05. And you could get super creative if you wanted, right? That would be between them two, right? You just can continue your digits as long as the 10 or the hundredths digit is between the 0 and the 1 that's there, or between the, I didn't quite say it right, between the 1.00 and the 1.10. If you're finding a decimal that's halfway between, like these, anytime you're wanting to find the halfway point of them, you're adding them together. Now, 0.9 repeating is equal to 1, so I'm going to use it as the number 1. I'm going to talk to you in a moment about what happens if they don't have a nice, beautiful 0.9 repeating, but it's something else that repeats, because you can't just change the number all the time. It just happened to work here, right? So if I take 1 and I take 1.1 and I add them together and divide by 2, I will be able to find my halfway point. So if I have this, I would get 2.1 divided by 2, and what is halfway in between? Yeah, 1.05. Really, we're just saying that halfway between $1 and $1.10 is $1.05, right? That's in terms of money. Now let me mention right here what happens when we are looking at this and we don't have this 0.9 repeating that we can turn into a 1 nicely. And we don't really want to turn it into a fraction because that would be really ugly to then add something together and divide by 2. That's not particularly useful either. So I'm going to make one up. We're going to flip screens over here and create kind of an additional example of the same variety. So the directions are all just the same. I just want to change my numbers. And these are arbitrary numbers that I'm picking. So I'm going to pick 0.35 repeating like this. So it means 35, 35, 35, 35, right? And we'll pick 0.36. Okay, totally arbitrary, just made them up. So when you're working with these numbers and they have this repeating form and you're trying to find a halfway location, it's actually not too bad to actually just expand the expression a little ways. I'm not going to tell you exactly how far, but if you do it probably 8 digits or something like that, you're probably sufficient. It might be sufficient before that. And then you're adding it to the 0.36. And you're dividing by 2. So this gives us the midpoint. If you're wanting simply just any number in between, you can again do the same thing that we had done before where we're just listing them out a few digits. I don't even know that I need that many. That's crazy. And my 36 can have some zeros on the end. So you need a number that's between 353 and 360. That's really what you're looking for. So you can do 0.354 or 0.355 or 0.356. You have lots of digits that you could do between them if you just expand their notations. So you can always expand their notations to ignore the fact that the repeating part, well, to minimize the fact that the repeating part is sort of irrelevant at some point when you're looking at the values, okay? It does continue, but it doesn't matter. I've already found something between. And then if I'm doing this one with my 3 5s and I'm adding them together and dividing by 2, let's see what happens. So I have 0.35, 35, 35, 35 added 8 times plus 0.36 and divide by 2. And once I do that, here's what I actually have on my calculator showing up. That's what shows up on my calculator when I did it. Did that show up on y'all's? Something like that? Yeah? Okay. Now, I know that's got this funny 5 at the end. Because it has rounded something because it's far enough out there. But before I get to the 5 at the end, if you want to erase the 5, you can. Do you see that there's another repeating thing showing up? Yeah, right? And that makes sense that could happen. So we actually have these, whoops, I didn't mean to do that. These numbers right here before it starts repeating, and the repeating part is just the 6, 7. So we have 0.35, and I have 6, 7 repeating, and that's actually the halfway location. So you can have a midpoint that's actually a repeating decimal in and of itself. Okay, so here's what I'm going to do. I'm going to do the last example with you, but I won't assign the homework. I'll give you the weekend off. So we'll do group work and we'll do the homework on Monday. We'll also move on to 7-4 on Monday, okay? But we'll do group work for 7-4 on Wednesday. We'll do group work for 7-3 on Monday, and it'll be assigned on Monday. Sound good? Okay. Our last example talks about, oops, back over here. Talks about something that you might not have thought to be true until I actually told you in this statement that it's true. Some addition problems are actually easier to compute with fractions. And some are easier to compute with decimals. So for example, 1/7 plus 5/7 is easy to calculate. Would you agree? What is it? 6/7, no problem. But 1/7 as a decimal is the repeating decimal, 0.142857 repeating, and 5/7 is 0.714285 repeating. And I don't know about you, but I don't really want to add those together. It's complicated. First of all, it's just got lots of digits. It's 6 digits long already. And what do I do about the repeating part? I haven't talked to you guys about what we really do much with repeating, except for that last example that I just made up over here, right? Where we sort of said, well, we're going to ignore it for a little while, and we're going to use our calculator and do this sort of, like hand-waving business. That's not easy to compute. But if you looked at the decimals 0.4 plus 0.25, that's pretty easy to compute in decimal form. But its corresponding fractional components, 2/5 plus 1/4, are not so easy to compute. Also true, right? So describe situations in which you think it would be easier to work with fractions than decimals and vice versa. When is it easy, in other words, to do it with fractions, and when is it not? When is it easy to do it with decimals, and when is it not? So can you throw out some things that make things easier or difficult, and we'll interpret your statement and put it in the right category. What do you notice?
Common denominator that it's easier to.
Awesome. So we like fractions when they have a common denominator. Do you guys agree with that? I do too. Common denominator makes it easy to work with fractions. And so if I'm making another list, right, for my decimals, it's not convenient, or I'm sorry, I didn't say that right way. If I make another list for my fractions for when it's not, I would include the fact that it's difficult when they have unlike denominators. Right? Tell me something about decimals. When are decimals easy? When are they not easy? Say it louder. Ah, yes. So if I'm dealing with decimals, I don't have much space in this slide. These are my smiley faces. They like them, right? Decimals are really nice when they are non-repeating, and we call that terminating. If they're terminating, they're easy to work with. And sometimes it can be terminating and it can have the same denominator, and that's just beautiful, and it works either way, and you're great with it. But sometimes it doesn't, right? And so then our decimals are not so good. We don't want to work with them by the flip side, right? When they are repeating, in terms of addition anyway. Does that make sense? So 1/3 is actually a really good example. 1/3 is easy to work with in fractional form, 1/3, but 0.3 repeating is not very easy to work with. And so we see kind of weird stuff show up when we have 0.3 repeating show up. That's a real common one we see. Any questions on that? Okay, so we're finished with 7.3. When I leave here, I'll go into Canvas and I'll adjust the due date. We will do group work for 7.3 on Monday, and we will have homework assigned on Monday to be due Wednesday. Okay, and we will move forward and start with 7.4 as well. Have a great weekend.